Hello everyone, I'm Arsha Niksa, and in today's video we'll cover the coding part for the forward Euler method. The focus of today's video would be the 13th problem of the IYPT 2020, the friction oscillator. So if you remember from our previous video, we got to a system of two equations, two ordinary differential equations, this one and this one. And in the previous video, we talked about how we could rewrite it in a way that we could use it for the forward Euler method. And based on that, we got to something similar to these two equations. So now we're going to use these two equations in order to find find x position of the rod in the friction oscillator. This is the center of rod here. The position of the rod as a function of time, and then we're going to plot it in Python. So without further ado, let's go to the coding part. So at first we're going to open a file. Let's call it let's call it friction oscillator.py. Alright, so now first let's think about what we are supposed to do. So in order to get the position as a function of time, we need a bunch of points like this. This one, this one, this one, this one, this one, this one. Let's say we need 100 points. So we have 100 of these, and we are interested in time 0 till time 10. Let's assume that the unit is in seconds. And we have an increment, or h, or delta t, of 1.1 seconds. So every 100 milliseconds, we want to know what the position of the rod is. And in order to plot these, we need, let's assume that the end is not inclusive, so it's like this. Our range is something like this. So as a result of this, we'll have 100 data points, and each of those data points are tuples which contain two numbers. The first member of the tuple would be the time, tn, and the second one would be the position, xn. So in order to store these tn's and xn's, we'll use something called an array. In non-precise terms, the array would be something like a list of numbers, or a matrix which is 1 by 100. So it's like this. 100 members, so to speak. So this would be our time array. And starting from the first one, we have T0, T1, T2, till T99. And similarly, for our position, we'll have another array, x0, x1, x2, x3, till x99. So what happens here is that we have 100 members, and basically in the simulation that we're going to have in the Python script, we're going to have an array that we fill with time. So this would be 0, 0.1, 0.2, and so on. And then we are going to start from our initial position, and at a time 0.1, using those two equations, we're going to calculate x1. Then we're going to calculate x2, and so on. So this is going to be the whole process for this problem. Alright, so in order to create an array, we are going to use a package called NumPy. So in order to import the package, we write import NumPy, and we write as np so that it would be shortened and it would be easier to call. So this is our first implementation. So we have a time array. So sorry, second. Yeah. So we have a time array. So in order to make a time array, we call NumPy. We say, hey NumPy, just give me a range. And the first argument would be the starting value. The second argument would be the ending value. And then we would have the step size, which was 0.1. But let's put these in variables so that they could be changed easier. So we have starting time, which is 0, ending time 10, and we have step size, which is 0.1. Now let's make this floating point. Alright, so starting time, ending time, and step size. So this is our range. We could print the range, time len time array. First, len gives us the length of the array. So let us run this. All right, so it gives us 100 members. So we're good up to now. So this is our time array. But what about our position array? So as for the position array, what we do is that we make an empty array. So a great way to make an empty array would be utilizing zeros, or an array full of zeros. Those zeros will be filled in later, but for now they are going to be zeros. That's their default value. So for that, we tell NumPy, hey, give us an array. An array of zeros. So, and then we give the number of zeros. So we have 100 members. So this is n, and yep, that's it. So this is our position array. So now what we have to do is that we have to give the position array its initial value, the x0, as its first element. So we tell Python, hey, as for your first value, note that Python is 0 base, so indexing starts from 0. Put the initial x. So we define a variable x initial, and let's say it would be 0.1 meters. So we put it here. So we gave it initial condition. Now what we have to do is that we have to start iterating. So in order to iterate on a list, a great way would be using a for loop. So we say, hey Python, for indexes, I stands for index, in the range of 0 to n, it means that, hey, create a range from 0 to n minus 1 inclusive, and give me i's, or those values in that range one by one. So it would give me 0, 1, 2, and so on. For I in range 0 to n, do a bunch of calculations. What were those calculations? Those two equations, discrete equations that we got. So in those equations, we had the position array I. By the way, we have to put this from 1 because we did fill the array with its initial value. So what we're interested in is starting from 1, not 0. So what we have to do is that we have to use those two functions. Let us get back to those functions. So yep, these two. So x of I, so let's rewrite that. So this would be x of I is equal to xi minus 1 plus h v I minus 1. So we have the position array in its previous index I minus 1 plus our step size h multiplied by our velocity. Now for the velocity, we're just going to put velocity array I minus 1, and then we're going to create the velocity array here. So it would be np zeros n, and again we're going to give it its initial value 0 v initial. Let us define a variable for the initial velocity. Let's say, I don't know, 0.1 meters per second. So yeah, this is the updated value of the position array, and we're going to what we do is that we get index I minus 1. So starting from 1, this would be 0. It gives us the 0th value of the position array. It adds it to the product of the step size and the velocity array at index I minus 1. Oh, so when we start from 1, that would be 0, and then it will go on till n minus 1. And then after calculating the result of this, it's going to save the result in the array at index I. This is an assignment operator. It basically assigns the value to the left-hand side, which is the ith index of the position array. So this is the position array, and as for the velocity array, I, we're going to have velocity array I minus 1 minus step size, a constant which we'll call alpha. I'll get to what alpha is later on, multiplied by our position array at the previous index. So let me explain what just happened. So let us shift the index by 1. So this would be vi is equal to vi minus 1 minus h. This is alpha x I minus 1. So this is what we used. Now we haven't defined alpha, so let's do so. Alpha was equal to 2 multiplied by g multiplied by mu divided by L. And so g is 9.8 and 81, and let's say mu is 0.5, and L, the length is, let's say, a meter. So yep, and then we get the velocity array. So again, we calculate the result of this and we assign the value to the velocity array. So now let us print the results. So position array and the velocity array. Let us print the time array as well. So let's run the code. Yep. This is the time array. It starts from 0 and it goes to 9.9 as expected. This is the position. So basically we've solved for the position using Euler's method, and we've got position at each of these times. And this is the velocity of the oscillating rod. So this is a little bit unintuitive since it's just numbers and you can't really make a sense of how the particle is moving with 300 numbers at the same time. So what we have to do is that we have to plot the results. So in order to plot the results, we have to type this. I'll explain what that means. So basically what I did was that I used a package called matplotlib. It's using for plotting stuff, and this package has many modules, and one of those modules is the pyplot module. So I called the pyplot module from the matplotlib package, and then told Python, hey Python, just call this PLT for me. So that was why I said as PLT. All right, so going back to the Python file. So I imported that. So in order to plot this, I say plt.plot time array. This is the array for the x-axis. And position array, this is the array for our y-axis. And then I'm going to say set the x label, the label of the x-axis as time, seconds, and plt.y label, position in meters. Now, of course, there are many other options available for plotting in Python, but that would be beyond the scope of this video. And at the end, I'm going to tell Python to show the plot. So now let us run the file. And yep, it looks something like this. Let us change the initial position. So let's say it's kind of in the center. What would happen then? And yep, this is how it would look. This is the end of the coding part. We've uploaded a great explanation about the Euler method, and we've also added an exercise for the Euler method on our GitHub repository. So you could check that out. You could find the forward Euler method in the Euler method directory of the GitHub repository, to which we'll leave a link in the description. And you could just check out the forward config.py section of it, and you could see the code and how it would work. And in the solver file, we've basically done the part about iterations. And you could basically take a look at these files and get an intuition about what we did in this video. So this is it for today's video. I hope you've enjoyed the video and could at least understand to some extent how the Euler method could be utilized to numerically solve differential equations. I hope you have a nice day, and bye.